Right now, somewhere beyond the orbit of Neptune, something is moving through the emptiness between stars, not toward us, not away from us, just passing through. It's not the first time this has happened, and it won't be the last. But this one is different, not because of what it is, because of what happened after we noticed it. In 2024, astronomers catalogued an object called 3I/Atlas, third interstellar visitor we've detected. The name tells you the order, nothing more. Standard procedure followed, observations began, data started flowing, and then, quietly, something shifted. Instruments were redirected, time was allocated, resources moved, the kind of attention usually reserved for something worth watching closely. But here's what's interesting. No major announcement followed, no dramatic press release, no conclusion offered to replace the questions. The updates just stopped. Not suddenly, not with explanation. They just faded into the background noise of ongoing science. And that's where things get curious. Because in a field built on published data and peer review, silence isn't neutral. It means something. We just don't always know what. This isn't a story about conspiracy or hidden knowledge. It's about something more fundamental. How we know what we know. How science decides what deserves explanation. And what it means when the universe offers us a hint but not a full picture. If you're curious about these kinds of questions, consider subscribing. It helps the channel keep exploring them. So let's begin with the most basic question, the one that shapes everything else. It's not what is 3I/Atlas. It's simpler than that. It's this. When does absence of information become information itself? Human understanding is shaped by what we notice. But even more, it's shaped by what we don't notice, what we can't notice. Our senses evolved to navigate a world of immediate distances, predators in the grass, fruit on branches, the movement of clouds before rain. We're built for that scale, for that speed, for those kinds of problems. But the universe doesn't operate at our scale. Most of what exists never announces itself clearly. It moves in ways we can't see, at speeds we can't feel, across distances we can't imagine. The light from distant stars takes years to reach us. By the time we see it, the thing that made it might have already changed, or died, or moved somewhere else entirely. We're always looking at the past, always making judgments based on incomplete information, and somehow we've built entire fields of knowledge on top of that limitation. Think about it this way. When you look at the night sky, you're not seeing the universe as it is. You're seeing how it was. Some stars you're looking at don't exist anymore. Some galaxies have already collided. Some planets have already formed or been destroyed. The present moment of the cosmos is hidden from us. We only get the echoes. Modern astronomy is built on this tension between curiosity and limitation, between what we want to know and what we can actually measure. We build instruments to extend our senses, telescopes that gather light our eyes can't see, detectors that track motion our brains can't process, computers that find patterns we'd never notice on our own. But here's the thing. These tools don't reveal everything. They reveal fragments, pieces of a larger picture that we have to assemble ourselves. Every observation is partial. Every measurement comes with uncertainty. Every conclusion rests on assumptions we don't always notice we're making. The universe doesn't present itself as a complete story. It offers hints, traces, suggestions of something larger, and we have to decide what those hints mean. That's not a flaw in the process. It's the process itself. Science doesn't work by collecting all possible information and then drawing conclusions. It works by collecting enough information to rule out some possibilities, by narrowing the field, by building models that work until they don't, and then refining them. Most of the time, this happens quietly. A paper gets published, data gets reviewed, new observations either confirm the model or challenge it. The conversation continues. That's how knowledge grows. Slowly, carefully, with a lot of back and forth between what's observed and what's understood. But every once in a while, something appears that doesn't fit neatly. Not dramatic enough to call a breakthrough. Not simple enough to ignore. Something that sits at the edge of what we expect. Just different enough to make you wonder. When that happens, attention shifts. Not just outward toward the object itself, but inward toward the methods we're using, the assumptions we're making, the boundaries of what we can actually claim to know. 3I/Atlas entered scientific awareness under ordinary circumstances. Telescopes scanned the sky. Algorithms flagged unusual motion. Astronomers reviewed the data. Initial classification followed standard procedures. It looked like an interstellar object. Third one we'd detected. The process seemed routine. Then instruments were adjusted. More observation time was allocated. Resources were directed toward tracking it more closely. That's where things get interesting. Not because redirection is unusual. It happens all the time. Telescopes are constantly being pointed at new targets. following up on preliminary findings, refining earlier measurements. But usually, when instruments are redirected, when observation intensifies, there's a reason that gets communicated: a paper, a briefing, an update to the research community, something that explains why the attention was worth it. This time, that didn't happen, not in the usual way. The public updates slowed, then stopped. No announcement explained the change. No conclusion replaced the initial classification. The object didn't disappear, the data didn't vanish, but the conversation around it just faded, and that raises a question. Not about what was found, about how we interpret the absence of explanation, about what it means when science decides not to say more. Is it because there's nothing more to say? Because the initial interest didn't lead anywhere worth reporting? Because the data turned out to be less significant than it seemed at first? Or is it because the analysis is still ongoing? Because conclusions haven't been reached yet? Because the process of turning observations into understanding takes longer than public curiosity allows? Or is it something else entirely? Something we don't have the context to interpret? The thing is, we don't know, and not knowing feels different depending on what we expect. If we expect transparency, silence feels like concealment. If we expect caution, silence feels like discipline. If we expect answers, silence feels like a void. But the universe doesn't owe us answers, and science doesn't operate on our timeline. What we're left with is a moment, a transition point, where observation shifted from routine to focused, and then from focused to quiet, where public attention briefly spiked and then moved on, where a name, 3i/Atlas, became a placeholder for something we can't quite define. This documentary isn't trying to fill that void with speculation. It's not here to invent meaning where none has been offered. It's here to understand the shape of the question itself, to explore what this moment reveals about how knowledge is formed, how observation works, how science balances curiosity with restraint, because the real story isn't about a single object moving through the outer solar system. It's about how we respond when the universe gives us something we don't fully understand, how we decide what's worth explaining, and what we do when the usual patterns of communication break down. To make sense of that, we need to start with something even more basic, not what happened with 3i/Atlas, but how we, as humans, experience uncertainty itself, how our minds handle gaps in information, how we fill in the blanks when the picture isn't complete. That's where we'll go next, not into telescopes or trajectories, but into perception, into the way we see what's missing, and why that matters more than we might think. Because before we can understand what science does with ambiguity, we need to understand what we do with it, how we react when patterns shift, when expectations aren't met, when silence replaces explanation, and that starts with the limits of human perception. We like to think we see the world as it is, that our senses give us direct access to reality, but that's not how it works, not even close. Your eyes don't show you everything. They show you what your brain decides is important, what it predicts should be there, what fits the patterns it's already learned. The rest gets filtered out, ignored, never even reaches your conscious awareness. It's not a flaw, it's efficiency. Your brain would be overwhelmed if it tried to process every photon, every sound wave, every shift in pressure and temperature around you. So it prioritizes, it builds models of the world based on past experience, and then it checks those models against incoming data. Most of the time, the model is good enough, close enough, and your brain just fills in the gaps. But sometimes, the model breaks. Something appears that doesn't fit, a pattern that shouldn't be there, or a pattern that should be there but isn't. That's when things get uncomfortable. Because your brain doesn't like uncertainty, it's built to resolve ambiguity as quickly as possible, to find explanations, to assign meaning, even when the evidence is incomplete. Even when the explanation is wrong, this tendency shows up everywhere, in optical illusions that exploit how your visual system predicts edges and motion, in the way you hear words in random noise if you're told what to listen for, in the way you see faces in clouds, patterns in static, intention in coincidence. Your mind is a pattern-finding machine, and it's really good at its job. Too good, sometimes. It finds patterns even when there aren't any. It constructs narratives even when the data is random. It fills in missing information with guesses that feel like certainty. And here's the critical part. You don't notice it happening. The gap between perception and reality feels invisible. The stories your brain tells you feel like direct observation. The conclusions you reach feel like logic, not interpretation. This is especially true when the information is incomplete, when there are gaps in the data, when the picture isn't clear, because gaps don't feel neutral, they feel meaningful. Like something's being hidden, like there's an answer just out of reach. Your brain doesn't like leaving blanks unfilled. It wants closure, resolution, a complete story. And if the real story isn't available, it'll construct one. This happens at every scale, In everyday life, when you assume someone's intentions based on limited behavior, in social situations, when you read meaning into silence or tone, in news cycles, when early reports get filled in with speculation before facts arrive, it's not malicious, it's automatic. Your brain is doing what it's designed to do, making sense of the world with whatever information is available. The problem is, in situations where information is genuinely limited, that process doesn't stop. It just works with less. And the less it has to work with, the more interpretation fills the space. Now apply that to astronomy, to objects moving through space at distances you'll never experience, at speeds you can't feel, on timescales that exceed human lifetimes. How do you perceive something like that? You don't. Not directly. You perceive data, numbers on a screen, graphs, light curves, orbital parameters, abstractions that represent something real but aren't the thing itself. Your brain isn't wired to understand those directly. It has to translate them into something familiar, something it can hold, and in that translation, something gets lost, or added, or shifted. Because the distances involved are beyond intuition, light years aren't something you can visualize accurately. You can say the words, you can know the number, but you can't feel it the way you feel the distance across a room or between cities. The same goes for velocity. When you hear that something is moving at tens of kilometers per second, your brain tries to anchor that to something, a car, a plane, a rocket. But those comparisons don't work. The scale is too different. The experience is too far removed. So your mind does what it always does. It simplifies. It approximates. It builds a mental model that's close enough to work with, even though it's not quite right. And when that model encounters something unexpected, like an object that gets more attention than usual, and then less, it tries to explain the shift. It looks for reasons, for patterns, for meaning. But here's the thing, the shift might not mean what your brain thinks it means. It might mean something operational, a change in priorities, a reallocation of resources, a decision based on factors you're not aware of, or it might mean nothing at all, just the normal ebb and flow of scientific work that doesn't get communicated publicly because there's nothing definitive to communicate yet. But uncertainty doesn't feel like that. It feels like a gap, and gaps feel like they should be filled. This is the psychological foundation underneath the whole question of 3i/Atlas. Before we even look at what was observed or how or why attention shifted, we have to acknowledge this. Our perception of the situation is filtered through cognitive processes that aren't neutral, that don't wait for complete information, that construct meaning, whether or not meaning is there. So when we ask why did the updates stop, we're not just asking a factual question. We're expressing a feeling, a sense that something is missing, that a pattern was interrupted, that closure wasn't provided, and that feeling is real, but it doesn't tell us what actually happened. It tells us how we respond to ambiguity. Now, does that mean the question isn't worth asking? No. It just means we have to ask it carefully, with awareness of our own biases, with recognition that discomfort with uncertainty is natural, but not necessarily informative. Because science operates differently than intuition. It doesn't rush to conclusions. It doesn't fill gaps with guesses. It waits. It tests. It refines. And sometimes it stays silent until there's something worth saying. That patience can feel frustrating from the outside, like something's being withheld. But from the inside, it's just discipline. The same discipline that keeps bad data from being published, that prevents preliminary findings from being treated as facts, that protects the integrity of the process. So before we go deeper into what happened with 3i/Atlas, we need to remember this. Our perception of the situation is shaped by how we handle incomplete information, and how we handle it isn't always rational, isn't always accurate, isn't always aligned with how science actually works. That doesn't make the question go away, but it does change how we approach it, with humility, with curiosity, and with recognition that the universe doesn't operate on human timescales, or according to human expectations. It just is, moving, changing, offering hints, and it's up to us to decide how to interpret them, or whether to wait until interpretation is actually possible. That waiting is hard, but it's also necessary, because rushing to meaning can obscure what's actually there, and sometimes the most honest answer is simply, we don't know yet. And that brings us to the next piece. Not how we perceive uncertainty, but how science identifies what's actually out there in the first place. How astronomers distinguish between objects that belong to our solar system and those that don't. How they recognize something as interstellar, and what that classification actually means. Because before we can understand why instruments were redirected toward 3i/Atlas, we need to understand how it was recognized as different in the first place, what makes an object interstellar, and how that determination is made. Imagine you're standing in a park, watching people move. Some are walking in circles, some are sitting still, Some are moving in straight lines at steady speeds. After a while, you start to notice patterns. The ones walking in circles are probably local, maybe exercising. The ones sitting are staying, but the ones moving in straight lines, not slowing down, not turning, those might be passing through, not part of the park's usual population, just visitors. That's basically how astronomers identify interstellar objects, by watching how they move, by tracking their trajectories, by calculating whether they're bound to the sun or just passing through. It's not about what they look like. Most objects in space are too far away to resolve any surface detail. You don't see shapes, you see points of light, dots on a dark background. What makes them distinct is motion, how they move relative to everything else. Our solar system has a structure. Planets orbit the sun in ellipses. Asteroids and comets do the same, though their orbits are often more stretched out, more eccentric, but they're still bound. Gravity holds them. They go around and around, pulled by the sun's mass. Interstellar objects are different. They're not bound. They're moving fast enough to escape the sun's gravity entirely. They come in from outside, swing past and keep going. They don't orbit, they don't return, they just pass through. Recognizing that difference comes down to velocity and trajectory. If you measure an object's speed and direction, you can calculate whether its motion is consistent with a closed orbit, one that curves back toward the sun, or an open trajectory, one that escapes into interstellar space. The math itself is well established. You measure position over time, you calculate velocity, you use that to determine the object's orbital energy. If the energy is negative, the object is bound. If it's zero or positive, it's unbound, free. But here's the complication. Those measurements aren't perfect. Every observation has uncertainty. Positions are measured to within a margin. Velocities are calculated from those positions, which means the uncertainty compounds, and orbital energy depends on velocity squared, so small errors in measurement can shift the conclusion. In practice, this means that early classifications are provisional. You might detect an object, measure its motion, and calculate that it's probably interstellar, but probably is doing a lot of work. You need more data, more observations over a longer time period, better constraints on the trajectory. That's why follow-up observations matter, why instruments get redirected, why resources get allocated to tracking something more carefully, because the initial classification is just the first step. It's an educated guess, not a final answer. 3I/Atlas was flagged based on its motion. The trajectory looked unbound, the speed looked high enough, the calculations suggested it came from outside the solar system. That's enough to call it interstellar, provisionally, enough to justify watching it more closely. But classification isn't a single moment. It's a process, one that continues as more data comes in, as the object moves further, as its path gets refined, and sometimes that refinement changes the classification. An object that looked interstellar turns out to be a long-period comet, or an asteroid with an unusual orbit, or something ejected from a planet's gravitational influence. The initial assessment was reasonable, but more data told a different story. Other times, the classification holds the object really is interstellar, but even then, there's more to learn. Where did it come from? How long has it been traveling? What's it made of? Those questions require different kinds of observations. Spectrometry to analyze its composition, photometry to measure brightness changes, long-term tracking to map its trajectory more precisely. Each of those observations takes time. Telescope time, instrument time, analysis time, and not every object justifies the full suite. Priorities have to be set, resources have to be allocated, decisions have to be made about what's worth pursuing. This is where things get complicated, because from the outside it might seem like every interstellar object should get maximum attention. After all, they're rare, they carry information from other star systems, they offer glimpses of environments we can't reach directly, but from the inside, it's not that simple. Telescope time is limited. There are more objects worth observing than there are hours to observe them. Comets, asteroids, exoplanets, supernovae, galaxies, black holes. Every field has its priorities. Every observation is a trade-off. So when an interstellar object is detected, the question isn't just, is this interesting? It's, is this interesting enough? Does it show unusual features? Does it challenge existing models? Does it offer data we can't get any other way? Sometimes the answer is yes. When Oumuamua was detected in 2017, it showed features that didn't fit expectations. Its shape seemed elongated. Its motion showed slight acceleration that couldn't be fully explained by outgassing. Those anomalies justified extensive follow-up. Papers were written, models were proposed. The conversation continued for years. Sometimes the answer is no. The object fits expectations. It behaves the way an interstellar rock should behave. It doesn't show surprising features. It's interesting in the sense that all interstellar objects are interesting, but it doesn't demand immediate intensive study, and sometimes the answer is, we need more time. The data so far is ambiguous, the features are unclear, the classification is uncertain, more observations are needed before any conclusions can be drawn. That last category is the hardest to communicate, because it doesn't offer closure, it doesn't provide a neat story, it just leaves the question open. Which brings us back to instruments being redirected, to resources being allocated, to observation intensifying, and then fading. Because that pattern doesn't tell you what was found, it tells you that something was considered worth checking, and then, at some point the checking either led somewhere, or it didn't. Or it led somewhere that hasn't been publicly communicated yet. The foundations of interstellar observation are simple in principle: measure motion, calculate energy, determine if the object is bound or free. But in practice, every step involves uncertainty. Every measurement is an approximation. Every conclusion is provisional until more data confirms it. And more data doesn't always arrive quickly. Sometimes it takes months, sometimes years. Sometimes the object moves out of range before enough observations can be made. Sometimes other priorities take precedence. Sometimes the analysis is still ongoing and there's nothing definitive to report yet. That's not evasion. It's just how the process works, how knowledge accumulates, how science decides when something is worth saying. So when we ask why updates stopped, we're asking a question that doesn't have a single answer. It could be operational, it could be evidential, it could be procedural, or it could be a combination of all three, filtered through systems of communication that aren't designed to keep the public updated in real time. Because real-time updates aren't how science usually works. Science works through papers, through peer review, through conferences and presentations, through processes that take time, that require verification, that don't rush to conclusions. Public communication is secondary. It happens when there's something worth communicating, when the findings are solid enough, when the story is clear enough, when the researchers are confident enough, and sometimes that confidence doesn't arrive on schedule. Sometimes the data stays ambiguous. Sometimes the analysis reveals more questions than answers. Sometimes the object just isn't as significant as it seemed at first, which leaves us here with an object that was noticed, that was watched, that prompted enough interest to redirect instruments, and then, quiet. That quiet doesn't mean nothing happened, it just means we don't know what happened, and not knowing is uncomfortable, but it's also honest, because the alternative is speculation, filling the gap with guesses, constructing narratives that feel satisfying but aren't based on evidence. And that's exactly what we're trying to avoid. So instead, we move forward, not by inventing answers, but by building context, by understanding how observation actually works, how instruments shape what can be known, how decisions are made about what to track, and how, and for how long. That's where we're headed next, into the practical realities of astronomical observation, the tools, the constraints, the trade-offs, the systems that determine what gets measured and what gets left behind. Astronomy doesn't happen in a vacuum, it happens through instruments, telescopes, detectors, systems built to gather specific kinds of light, at specific wavelengths, under specific conditions. And every one of those systems has limits. You can't observe everything, you can't track every object, you can't allocate time to every question. Choices have to be made, and those choices shape what we know. Let's start with something simple, a telescope. You point it at a patch of sky, you collect light, that light gets focused, measured, recorded, sounds straightforward, but here's what's actually happening. You're not seeing the sky as it is, you're sampling it, choosing one region out of billions for a specific duration, at a specific resolution, with a specific instrument that's sensitive to some wavelengths and blind to others. Every observation is a trade-off, between field of view and resolution, between depth and speed, between wavelength coverage and sensitivity. You can't optimize everything at once. You have to choose what matters most for the question you're asking. And the questions change, constantly, as new objects are discovered, as priorities shift, as instruments become available or unavailable, as data from other sources suggests new targets worth investigating. This is why observation schedules are dynamic, why time gets reallocated, why something that seemed important last month might not justify continued tracking this month, not because the object changed, but because the context did. Telescope time is a finite resource. There are more requests than can be accommodated. Committees review proposals. They prioritize based on scientific merit, feasibility, and broader impact. They allocate hours, sometimes days, rarely weeks, almost never continuously. So when an object like 3I/Atlas gets detected, the first question is, does this justify more time? How much time? With which instruments? For how long? The answer depends on what the initial data showed. If there's something unusual, unexpected brightness, strange motion, spectral features that don't fit models, then yes, more time gets allocated. Follow-up observations are scheduled, resources are redirected. If the data looks normal, consistent with what you'd expect from an interstellar rock or comet, then follow-up might still happen, but with lower priority. A few additional observations to refine the trajectory, maybe some spectroscopy if there's time, but not intensive, long-term monitoring, and sometimes the answer is uncertain. The data hints at something interesting, but it's not clear yet, so you allocate moderate resources, you keep watching, you collect more data, and you wait to see if the pattern clarifies. That's the stage where redirection happens, where instruments get pointed at something new, where observation intensifies, not because a discovery has been made, because a question has been raised. But here's the critical part. Redirection doesn't mean sustained focus. It means temporary reallocation. A shift in priorities that lasts as long as the question seems worth pursuing. Once the data comes in, once the analysis begins, the intensity often decreases. The object gets moved to routine monitoring, or dropped from the schedule entirely. From the outside, that can look significant, like something was found and then hidden. But from the inside, it's just normal workflow. You gather the data you need, you move on to the next target. You come back to the analysis later, when there's time to process it properly. Because observation and analysis are separate stages. Observation happens in real time. You point the telescope, you collect the photons, you record the data, but analysis takes longer, much longer. You have to calibrate the instruments, correct for atmospheric effects, remove noise, extract signals, compare to models, run simulations, test hypotheses. That process doesn't happen instantly. It happens over weeks, months, sometimes years. And it doesn't happen in public. It happens in labs, in offices, in collaboration meetings. It produces drafts, revisions, internal reports, not press releases. So when public updates stop, it doesn't mean the work stopped. It just means the work moved into a different phase, one that's less visible, less immediate, less suited to public communication. And sometimes that analysis doesn't produce a clear result. The data is ambiguous. The signal is weak. The models don't converge. You can't say anything definitive, so you don't say anything at all. Not yet. Not until there's something worth saying. This is where the gap between scientific process and public expectation becomes most apparent, because the public expects updates, regular communication, explanations for why attention shifted, conclusions that match the initial interest. But science doesn't work that way. It works in bursts: observation, then silence, data collection, then analysis, questions, then long pauses while answers are being worked out. And those pauses don't get narrated, they just happen. Meanwhile, the instruments move on to the next object, the next question, the next allocation of time, because there's always something else worth observing, always another target, always limited resources and infinite curiosity. So the fact that 3i/Atlas stopped being the focus doesn't tell you much. It tells you that the initial observations were completed, that the data was collected, that the instruments were needed elsewhere, but it doesn't tell you what the data showed, or what conclusions, if any, were reached, or whether the analysis is ongoing, or finished, or stalled. All of that happens behind the scenes, in the space between observation and publication, in the months or years it takes to turn raw data into knowledge that can be defended, reviewed, and shared. And sometimes that knowledge never arrives, not because it was suppressed, but because the data didn't support strong conclusions, because the signal was too weak, because the object wasn't as unusual as it seemed, because other explanations fit just as well. That's not failure, that's just how exploration works. You look, you measure, you analyze, and sometimes you find something, sometimes you don't. Sometimes you find something, but you can't be sure what it means yet. And when that happens, you don't rush to publish. You don't make claims you can't support. You wait. You gather more data if you can. You refine your models. You test alternative explanations. You hold the question open until the answer is solid enough to stand on. That discipline is essential. It's what separates science from speculation, what keeps bad ideas from spreading, what ensures that when something is announced, it's been checked, tested, and verified, but it also creates silence, long stretches where nothing is said because nothing can be said with confidence, where the work continues but the communication doesn't. And from the outside, that silence feels like a gap, like something missing, like an answer that should be there but isn't. But from the inside, it's just patience. The slow, careful process of turning observations into understanding, of waiting until the picture is clear enough, of resisting the urge to fill gaps with guesses. So when we ask why instruments were redirected toward 3i/Atlas and then stopped publishing updates, we're asking a question that assumes a certain kind of process, one where observation leads directly to communication, where attention implies significance, where silence implies concealment. But that's not the process we're dealing with. We're dealing with one where observation leads to data, where data leads to analysis, where analysis takes time, where communication happens only when there's something defensible to communicate. And if that hasn't happened yet, it doesn't mean nothing was found. It means nothing publishable was confirmed, nothing solid enough, nothing that meets the standards required, which leaves us in this moment, with an object that passed through, with instruments that watched, with data that exists somewhere, in some form being processed or filed or waiting for the right context to matter, and with silence, not the silence of conspiracy, but the silence of work that isn't finished yet, of questions that haven't resolved, of a process that doesn't move at the speed of public curiosity. That's the reality of observation, of measurement, of science, as it actually operates, not dramatic, not immediate, just careful, patient, waiting for certainty before speaking. And that brings us to a moment of transition, where observation shifted from active to passive, where attention redirected and then faded, where something changed, even if we don't know exactly what, because there was a point where the pattern shifted, where public updates slowed, where the object stopped being mentioned in the usual channels, and that shift happened for a reason, even if the reason isn't clear. So let's look at that moment, not to invent meaning, but to understand what transitions like this actually signify, how workflows change, how priorities evolve, how science moves from one focus to another, without always explaining why. There's a rhythm to scientific observation, a cadence. New objects get detected all the time. Some get logged and archived. Some get flagged for follow-up. Some get intensive study. And then gradually, attention moves elsewhere. It's not random, but it's not always transparent either. Decisions get made based on internal assessments, on data that hasn't been published yet, on criteria that aren't always communicated to the public. And sometimes, those decisions involve stepping back, reducing observation intensity, moving an object from active monitoring to routine cataloging, not because it's unimportant, but because the immediate questions have been addressed, or because they can't be answered with current data, or because other targets have become more pressing. That stepping back is a normal part of the process. It happens all the time. Most objects don't justify long-term intensive study. They get observed, they get classified, they get added to the catalog, and that's it. But when an object gets initial attention, when it's flagged as potentially interesting, when instruments get redirected, when resources get allocated, the stepping back can feel different, like a reversal, like something changed that we're not being told about. And maybe something did change. Maybe the initial data didn't pan out. Maybe the follow-up observations were less interesting than expected. Maybe the analysis revealed that the object was more ordinary than it seemed. Or maybe nothing changed. Maybe the data is still being analyzed. Maybe the conclusions are still being worked out. Maybe the researchers just aren't ready to say anything yet. We don't know, and not knowing leaves us with a question. What does this transition mean? What does it tell us? One interpretation is procedural. The observation cycle completed. The data was collected. The resources were needed elsewhere. The object moved into a different phase of tracking, less intensive, more routine. That's normal. That's how these things go. Another interpretation is evidential. The follow-up data didn't reveal anything significant. The object looked like a standard interstellar rock. No unusual features, no anomalies worth reporting. So attention moved on. That's also normal. A third interpretation is that the analysis is ongoing. The data exists. It's being processed. But it's complex, or ambiguous, or incomplete, so nothing has been published yet. That's normal too. All three of these interpretations are consistent with what we observe. Instruments redirected, data collected, updates stopped, no major announcements. Just a quiet shift from active to passive. But here's the problem. We don't know which interpretation is correct. We don't have access to the internal assessments. We don't see the data. We don't hear the discussions. We just see the pattern from the outside. And patterns by themselves don't tell you causes. They tell you effects. They show you what changed, but not why. So when we try to understand this moment of transition, we're working with incomplete information. We can describe what happened. Observation intensified, then faded, but we can't explain it with certainty. That doesn't mean we should ignore it, but it does mean we should be careful. We should consider multiple possibilities. We should acknowledge the limits of what we can actually infer. Because the truth is, transitions like this happen all the time in science. Objects get detected, they get studied, they get set aside. Sometimes there are papers, sometimes there aren't. Sometimes the findings are significant, sometimes they're not. Sometimes it takes years before anyone knows for sure, and in that space between detection and conclusion, there's often nothing. Just work, just analysis, just the slow process of turning observations into knowledge. No updates, no announcements, no public communication. That space feels empty from the outside, but from the inside, it's full of effort. Data being processed, models being tested, hypotheses being refined, questions being asked and re-asked, and held open until the answers are clear. So the moment of transition we're observing might not be a moment at all, it might just be the beginning of that space. The shift from observation to analysis, from public visibility to internal work. And if that's the case, then the silence isn't hiding anything. It's just the normal quiet of science in progress, of work that isn't ready to be shared yet, of conclusions that haven't been reached. But there's another possibility, one that's harder to evaluate without more context, which is that the transition represents something else, a decision not just to reduce observation intensity, but to reclassify the object entirely, to move it out of the category of worth tracking and into the category of logged and archived. That would imply that whatever initial interest existed has been resolved, that the questions have been answered or deemed unanswerable, that the object no longer justifies resources. If that's the case, then the lack of public communication might simply reflect the fact that there's nothing noteworthy to report. The object was interesting enough to check. It was checked. It turned out to be unremarkable. End of story. That's a perfectly reasonable explanation. It fits the pattern. It doesn't require any assumption of secrecy or concealment. It just acknowledges that most observations don't lead to groundbreaking discoveries. Most lead to confirmation of existing models, to incremental refinement of catalogues, to data points that contribute to larger statistical analyses. And those kinds of results don't usually generate press releases. They generate entries in databases, lines in tables, background information that future researchers might use but that don't warrant their own spotlight. So it's possible that 3i/Atlas is exactly that, an entry in a database, a confirmed interstellar object, unremarkable in behavior, consistent with expectations, interesting in the abstract, but not in the specific. If that's true, then there's no mystery, just a routine observation that played out normally. The redirection of instruments was standard follow-up. The silence is standard workflow. The absence of updates reflects the absence of anything unusual to report. But we can't confirm that, because confirmation would require access to the data, to the analysis, to the internal reports and assessments that shape how objects get classified and prioritized. And we don't have that access. We just have the pattern, the shift, the quiet. So we're left with possibilities, not answers. Interpretations that fit, but can't be verified. Explanations that make sense, but remain provisional. And that's okay, because this isn't about solving a mystery. It's about understanding how knowledge forms, how science decides what to communicate, how transitions happen between observation and conclusion, and how silence by itself doesn't tell us much. It just tells us that something shifted, and that the reasons for that shift are known to the people doing the work, but not necessarily to us. Which brings us to the next layer, context. Because 3i/Atlas didn't appear in isolation. It's part of a larger picture, a population of objects, a field of study, a cosmic process that extends far beyond any single detection, and understanding that larger picture helps us see why individual objects might not always warrant prolonged focus, why attention moves on, why some discoveries matter more than others. Because the universe is full of things passing through, full of objects ejected from other systems, full of material drifting between stars, and detecting one of those objects by itself isn't extraordinary. It's expected. The question is always, what does this particular object tell us that we didn't already know? And if the answer is not much, then it makes sense for attention to shift elsewhere. So let's widen the lens. Let's place 3i/Atlas within the broader context of interstellar phenomena, within the systems of motion that define how matter moves through space, within the expectations scientists have about what should be out there and how often it should appear, because context changes everything. It changes how we interpret absence, how we assess significance, how we understand what silence might mean, and that's where we're headed next. The universe is not empty. That's the first thing to understand. Between stars, across galaxies, through the vast reaches of what we call interstellar space, there's matter, dust, gas, rocks, ice, radiation, magnetic fields, particles moving at every conceivable speed. Most of it stays where it is, gravitationally bound to stars, to planets, to clusters, but some of it doesn't. Some of it escapes, gets ejected, flung out by close encounters, by stellar explosions, by gravitational slingshots around massive bodies, and once it's free, it drifts for millions of years, billions, crossing distances that dwarf anything we can imagine. Our solar system is moving through this environment, orbiting the center of the Milky Way at about 230 kilometers per second, which means we're constantly encountering material that doesn't belong to us, that originated somewhere else. That's passing through our neighborhood on its way to nowhere in particular. Most of that material is small, dust grains, molecules, things too tiny to detect individually, but occasionally something larger passes through, a rock, a comet, an object big enough to reflect sunlight, big enough to notice. Statistically, this should happen, not often, but regularly enough that over time, as our detection methods improve, we should start seeing these objects, and we have. Oumuamua in 2017, Borisov in 2019, 3I/Atlas in 2024. 3 confirmed interstellar objects in less than a decade. That's not anomalous. That's roughly consistent with models that predict how often material ejected from other star systems should cross our path. The models themselves are based on a few simple ideas. Stars form in clusters. Those clusters are chaotic. Gravitational interactions between young stars and their surrounding material lead to ejections, rocks, comets, planetesimals that didn't quite form planets. All of that gets scattered. Most of it stays within the original system, but some fraction escapes, gets flung out into interstellar space, and once it's out there, it's just drifting, moving in more or less straight lines, crossing the galaxy over timescales that make human history look like a blink. Our solar system is one of billions, each one contributing to this background population, each one occasionally ejecting material, each one in turn occasionally intercepted by material ejected from somewhere else. So when we detect an interstellar object, we're not seeing something unnatural, we're seeing a prediction confirmed, a process we expected finally becoming visible because our instruments are good enough. That's the context. 3I/Atlas is part of a population, not an anomaly, not a signal, just a sample. One instance of a process that's been happening for as long as stars have existed, and that changes how we think about it. Because if it's one of many, then the significance of any individual object decreases. What matters isn't the object itself. What matters is what it tells us about the population, about the distribution, about the properties shared across many objects, not just this one. That's why some interstellar objects get more attention than others. Oumuamua got attention because it was the first, because it showed unusual features, an elongated shape, slight non-gravitational acceleration. Those features raised questions, made it worth studying intensively. Borisov got less attention because it looked like a comet, a normal comet, just from somewhere else. It had a tail, it outgassed, it behaved the way we expect comets to behave. Interesting. Yes, but not mysterious, not anomalous. 3I/Atlas falls somewhere in between, confirmed as interstellar, but not, apparently, showing features dramatic enough to warrant the level of sustained public communication that Oumuamua received. That doesn't mean it's unimportant. It means it fits expectations. It contributes to the catalogue. It adds one more data point to the population, but it doesn't challenge models, doesn't force revisions, doesn't make us rethink what we know. And objects that don't challenge models tend to fade from public view, not because they're being hidden, but because there's nothing particularly newsworthy to report. They become part of the background, part of the growing dataset that future studies will draw on. This is how science builds knowledge about populations, not by studying every individual in exhaustive detail, but by gathering enough samples to see patterns, to measure distributions, to test whether observations match predictions. Interstellar objects are still rare in our detection record, 3 confirmed so far, but that number will grow as telescopes improve, as surveys become more comprehensive, as algorithms get better at flagging unusual motion. In a decade, we might have dozens, in a century, hundreds, and as that catalogue grows, individual objects will matter less. The population will matter more, the statistics, the averages, the outliers. Right now, we're in the early phase, where each detection feels significant because the sample size is so small, but eventually that will change. Detection will become routine, follow-up will become selective. Resources will be allocated to the objects that stand out, not to every object that passes through. And 3I/Atlas might simply be one of the first to experience that shift. Detected, classified, logged, but not singled out for intensive study because it didn't show features that demanded it. That's a reasonable interpretation, one that fits both the pattern of observation and the broader scientific context. It doesn't require assuming secrecy, it just requires acknowledging that not every detection is equally significant. But there's another layer to this, which is that we don't just care about individual objects, we care about what they represent, what they carry, what they might tell us about the places they came from. because every interstellar object is, in a sense, a messenger. It formed somewhere, around some star, in some system, and it carries information about that environment, its composition, its history, the conditions that shaped it. If we could analyze that information in detail, we'd learn about star systems we can't visit, about planetary formation processes happening light years away, about the diversity of materials and environments across the galaxy. That's the real prize, not the object itself, but what the object can teach us. The problem is, getting that information is hard, really hard. Most interstellar objects move too fast. They pass through the inner solar system quickly. By the time we detect them, they're already on their way out. We get a brief window, days, weeks at most, and then they're too far away to observe in detail. So we're limited. We can measure trajectories, brightness, basic spectral features if we're lucky, but we can't land on them, can't sample them directly, can't bring them back for analysis, which means that most of what we learn is statistical, aggregated over many objects, not deep dives into individual cases. And that's fine, that's how a lot of astronomy works. You study populations, you measure distributions, you look for trends, and slowly, over time, a picture emerges. But it also means that when an individual object doesn't show anything unusual, it just becomes part of that larger data set. A point on a graph, a number in a table, useful but not headline-worthy. So if 3i/Atlas turned out to be ordinary, consistent in composition, unremarkable in motion, fitting within expected parameters, then its role shifts, from potentially interesting anomaly to confirmed population member. Both are valuable, but only the first justifies intensive, prolonged observation, and that shift might be exactly what we're seeing. The transition from anomaly checking to population cataloging, from let's study this closely to let's record it and move on. If that's the case, then the silence makes sense, because there's no discovery to announce, no anomaly to explain, just confirmation that the universe is behaving the way we thought it would. That's not exciting, but it's important, because confirmation matters. It tells us our models are working, that our predictions are sound, that the universe is, at least in this respect, understandable. And maybe that's the real takeaway here. Not that something mysterious happened with 3i/Atlas, but that the universe is full of these objects, that we're getting better at detecting them, and that most of them, most of the time, will be unremarkable, which doesn't make them unworthy of study. It just makes them part of the background, part of the ongoing work of cataloging, measuring, and understanding the cosmic environment we're embedded in. So when we place 3i/Atlas within this larger context, within the population of interstellar objects, within the systems of galactic motion, within the expectations shaped by decades of modeling, it starts to look less like an isolated event and more like a normal occurrence, expected, routine, one of many. And if that's true, then the absence of updates isn't a gap. It's just the natural rhythm of science. Detect, classify, catalog, move on. But even with that context, there are still edges, still limits to what we know, still questions that remain open, even after classification. And those edges matter, because they define where understanding ends and speculation begins. So let's turn toward those edges, not to fill them with guesses, but to acknowledge them, to map the boundaries of what's knowable and what isn't, to see what remains unresolved and why. There's always more we don't know than we do. That's not a flaw. It's the nature of inquiry. Every answer opens new questions. Every measurement reveals new uncertainties. Every model has limits. With interstellar objects, those limits are especially clear, because the objects themselves are fleeting, because we can't interact with them directly, because most of what we'd like to know requires data we can't collect. Take composition. We'd like to know what 3i/Atlas is made of. Rock, ice, metal, some combination? That information would tell us about the environment it formed in, about the star system it came from, about the processes that shaped it. But getting that information requires spectroscopy, detailed analysis of the light it reflects or emits, and that requires the object to be bright enough, close enough, and observed with the right instruments at the right time. If those conditions aren't met, if the object is too faint, too far, moving too fast, then we can't get reliable composition data. We can guess, we can infer based on brightness and color, but we can't know. The same applies to origin. We'd like to know where 3i/Atlas came from, which star system, which direction, how long it's been traveling. That would help us understand the dynamics of interstellar ejection, the pathways material takes through the galaxy. But reconstructing origin requires precise trajectory data, extended observations, backtracking motion through complex gravitational fields, and even then the answer is probabilistic, not certain. We can say this object probably came from this general region of the galaxy, but we can't point to a specific star and say it came from there. the uncertainties are too large, the timescales are too long, so we're left with questions. Good questions, interesting questions, but questions nonetheless. And those questions don't always get answered, not because someone's hiding the answers, but because the answers aren't accessible, the data doesn't exist, the methods aren't precise enough, the object has already moved on. This is one of the hardest things to communicate about science. The fact that not every question can be answered, that some things remain uncertain, that knowledge has edges, and those edges are often fuzzy. The public expects closure, expects that if instruments were redirected, if observation intensified, then answers must exist, that someone somewhere knows what's going on, but that's not always true. Sometimes the observation reveals nothing conclusive, sometimes the data is ambiguous, sometimes the analysis produces results that are interesting but not definitive, and when that happens, what do you say? How do you communicate uncertainty without sounding evasive? How do you explain that the question was worth asking, but the answer isn't clear yet? That's a communication problem, not a scientific one. Science is comfortable with uncertainty. It builds uncertainty into every measurement. It quantifies it. It works with it. It doesn't pretend to know more than the evidence supports. But public communication doesn't have the same tolerance. Uncertainty feels like hedging, like avoiding commitment, like something's being held back. So scientists often wait. They wait until the uncertainty is reduced enough, until the conclusions are solid enough, until they can say something with confidence. And if that never happens, if the data stays ambiguous, then they often say nothing at all, not out of secrecy, but out of discipline, out of respect for the standards that keep science credible. That discipline is essential. It's what prevents premature announcements, what stops speculation from being presented as fact, what protects the integrity of the process. But it also creates gaps, periods where questions are open, but answers aren't ready, where work is ongoing, but communication is silent, where the public is left wondering, and scientists are still working it out. 3i/Atlas might be in one of those gaps, where the initial observations raised questions, where follow-up data was collected, where analysis is ongoing or completed but inconclusive, where nothing definitive has emerged yet. If that's the case, then the silence isn't hiding anything. It's just waiting for clarity, for confidence, for something worth saying. And that waiting can take a long time, longer than public attention spans, longer than news cycles, longer than the initial curiosity lasts. By the time the analysis is done, by the time the conclusions are ready, the moment has often passed. The object is no longer in the headlines. The public has moved on, and the results, when they're published, go into journals, into databases, into the background knowledge of the field. They don't generate press releases. They don't recapture attention. They just add to the slow accumulation of understanding that defines how science actually works. So the edges of knowledge aren't dramatic. They're quiet. They're the spaces where questions remain open, where data is still being processed, where conclusions are still being tested. And those spaces are frustrating for everyone, for the public, who wants answers, for the scientists, who want certainty, for the process itself, which doesn't move as fast as anyone would like, but they're also necessary, because rushing past them leads to error, to claims that don't hold up, to conclusions that have to be retracted. Better to wait in the uncertainty than to leap to false certainty. And that's where we are, with 3i/Atlas, at the edge, where what's known meets what's not, where observation has been completed, but interpretation is still unfolding, where silence reflects not concealment, but patience. And patience in science is often the most honest response. So what does this tell us? Not about 3i/Atlas specifically, but about the universe, about observation, about the process of knowing. It tells us that the universe doesn't perform for us, doesn't reveal itself on demand, doesn't organize its phenomena into tidy narratives that fit our expectations. It just is, moving, changing, indifferent to whether we understand it or not. And our attempts to understand it are always partial, always constrained, always shaped by the tools we have, the time we can allocate, the questions we think to ask. We build instruments, we point them at the sky, we collect data, and we hope that somewhere in that data there's meaning. Something that tells us about how the universe works, about where we fit within it. Sometimes we find it, sometimes we don't, and sometimes we're not sure yet. That uncertainty is built into the process. It's not a failure, it's a feature. Because if we only studied things we already understood, we wouldn't learn anything new. The edges are where discovery happens, where assumptions get tested, where models get refined. But discovery doesn't always look dramatic. Often it's incremental, subtle, a small shift in parameters, a slight adjustment to expectations, a confirmation that yes, the universe behaves the way we thought it did. And those small shifts don't make headlines. They just make the foundation of knowledge a little more solid, a little more reliable. 3i/Atlas, whatever it turns out to be, is part of that process. One observation among many, one data point in a larger data set, one object that passed through, got noticed, and now contributes to the ongoing effort to understand how matter moves through the galaxy. That's valuable, even if it's not dramatic, even if it doesn't come with a press release, even if the public never hears the final conclusions. Because science isn't about spectacle, it's about building understanding, slowly, carefully, with attention to detail and respect for evidence. And that process requires patience, both from the people doing the work and from those of us watching from the outside. So when we ask what this moment reveals about the universe, the answer isn't about 3i/Atlas. It's about process, about how knowledge forms, about the difference between observation and understanding, about the long, quiet work that happens between detection and conclusion. It reveals that the universe is knowable, but not easily, not quickly, not completely. It reveals that our tools are powerful, but limited, that we can measure motion and collect light, but we can't always extract meaning from what we measure. It reveals that science is disciplined, that it waits for evidence, that it doesn't rush to fill gaps with speculation, and it reveals that uncertainty is okay, that not knowing for now is better than pretending to know, that the edges of knowledge are where the real work happens. Those lessons don't resolve the question of 3i/Atlas, but they help us hold the question differently, with less urgency, with more patience, with recognition that the absence of answers isn't the same as the absence of work. And that brings us to the final piece. Not what this means for the universe, but what it means for us, for how we relate to uncertainty, for how we navigate a world where not everything is explained, where gaps exist, where silence is sometimes the most honest response. We live in a time of constant information, constant updates, constant communication. We've become accustomed to immediate answers, to explanations that arrive as fast as the questions. But the universe doesn't work that way. It operates on timescales that dwarf human impatience. It unfolds according to processes that don't care about our curiosity. And science, when it's done well, mirrors that patience. It doesn't rush. It doesn't perform. It just works. Slowly, carefully, with attention to detail that often goes unnoticed. That mismatch between our expectations and the reality of how knowledge forms creates tension. We want answers. We want them now. We want them to be clear, complete, and satisfying. But what we get instead is fragments, provisional conclusions, ongoing analysis, silence where we expected explanation, and that feels uncomfortable. It feels like something's being withheld, like we're not getting the full story. But what if the full story isn't available yet? What if the work is still happening? What if the conclusions haven't been reached? Then the discomfort we feel isn't about what's being hidden. It's about our relationship with uncertainty, with incompleteness, with the reality that not everything can be known immediately. And that's worth sitting with, because it's not unique to 3i/Atlas. It's everywhere, in every field, in every aspect of life where complexity exceeds our ability to grasp it quickly. We're surrounded by things we don't fully understand, systems too complex to model perfectly, processes too slow to observe completely, questions too difficult to answer definitively. And we have a choice. We can fill those gaps with speculation, with narratives that feel satisfying but aren't based on evidence, with conclusions that provide closure but might be wrong. Or we can sit with the uncertainty. We can acknowledge that not knowing is okay, that the absence of answers doesn't mean the absence of effort, that patience is sometimes the most honest response. 3i/Atlas, in that sense, becomes a mirror. It reflects back how we handle incompleteness, how we respond when the universe doesn't explain itself, how we navigate the space between curiosity and understanding. And what it shows us is that we're not great at waiting. We're not comfortable with silence. We want resolution. We want closure. We want the story to make sense. But the universe doesn't owe us that. It doesn't organize itself into narratives. It doesn't provide explanations on demand. It just is. And our job isn't to force it into stories that satisfy us. Our job is to observe, to measure, to think carefully, and to wait until understanding is earned, not assumed. That's hard, especially in a culture that rewards speed, that values confidence, that treats uncertainty as weakness. But it's necessary, because the alternative is worse. The alternative is pretending to know more than we do, filling gaps with guesses, constructing narratives that feel true but aren't supported by evidence, and that doesn't serve anyone, not the public, not the scientists, not the process of understanding itself. So what does 3i/Atlas mean for us? It means we need to get better at sitting with uncertainty, at respecting the limits of what we know, at trusting the process even when it doesn't move at the speed we'd like. It means recognizing that silence isn't always evasion, that absence of updates isn't the same as concealment, that gaps in communication might just reflect gaps in understanding, and it means holding space for the possibility that some questions take time, that some answers aren't ready yet, that some moments require patience instead of conclusions. That's not satisfying, but it's honest. And in a world full of narratives constructed to provide closure, honesty matters, because what we're really asking when we ask about 3i/Atlas isn't what is this object, it's how do we navigate a universe that doesn't explain itself. And the answer to that question isn't a fact, it's an orientation, a way of being in relationship with uncertainty, a willingness to hold questions open when the evidence doesn't support closing them. That's what this moment teaches us, not about interstellar objects, but about ourselves, about how we know, about how we wait, about how we resist the urge to fill every gap with meaning. And maybe that's the most important lesson of all. That understanding isn't about having all the answers. It's about asking the right questions and being patient enough to let the answers emerge when they're ready. So we're left here with an object that passed through, with instruments that watched, with data that exists somewhere, being processed or filed or waiting for context, and with silence. The kind of silence that doesn't shout, that doesn't hide, that just waits. It's not a dramatic ending. It's not a revelation. It's just the space where questions live, when answers aren't ready yet. And that space is okay. It's where science happens, where knowledge grows, where patience is practiced and understanding, eventually is earned. 3i/Atlas moved through our solar system and out the other side. It was noticed, it was watched, and now it's gone. Moving through the darkness between stars, carrying whatever information it holds beyond our reach. We collected what data we could, we asked what questions we were able to ask, and now we wait for analysis, for conclusions, for whatever understanding eventually emerges. If that understanding comes, it'll arrive quietly, in a paper, in a database, in the slow accumulation of knowledge that defines how science works. And if it doesn't come, if the data stays ambiguous, if the questions remain open, then we'll have learned something anyway, about the limits of observation, about the edges of knowledge, about what it means to encounter something we can't fully explain, and we'll keep watching, keep measuring, keep asking, because that's what we do. We look up, we notice, we wonder, and sometimes that's enough. If you found this exploration worth your time, consider sharing it with someone who appreciates questions more than answers. And if you want to keep thinking about these kinds of ideas, there's more waiting for you. Thanks for staying curious.